So in this video, I'm asked to prove that n squared is less than n factorial for n greater than 4 when, of course, n belongs to the set of integers. Okay, so this is obviously a proof by induction because I'm dealing with integers and I'm dealing with some discrete amounts here. So in this case, I have an inequality. So it's an induction, so I need to do my two steps, right? So my first step is my basis step, where I want to show that the smallest value of n is true for this statement. By the way, this statement I can call this statement Pn. Okay, so my basis step is basically showing that the smallest value of n defined in the question works for p. So in other words, in this case, my smallest value of n that should work for p is n equal 4, because this is a greater than or equal. So n is at the least 4. So my basis step is n equal 4. And so what I'm trying to do, I'm trying to prove that P4 is true. P4 is true. Okay. So I'll just take my two sides. So 4 squared is 16, and 4 factorial is, if you don't remember what the factorial is, 1 times 2 times 3 times 4, and that's 24. And so clearly 24 is greater than 16, so 4 factorial is greater than or equal to 4 squared. So P4 is true. P4 is true. Hence, the base case has been proven. Okay, so that's my first step. That's the basic step. Okay. My second step is a bit more complicated, as you know, so that's my inductive step. Okay, so in the inductive step, I assume Pn is true. Pn is true. i.e., I'm assuming that n squared is less than or equal to n factorial for n greater or equal to 4. So this is what I'm assuming. Now my goal is to prove that Pn plus 1 is true. i.e., that is, I'm trying to show that n plus 1 squared is less than or equal to n plus 1 factorial. So how do I do this? Well, this is always the more complicated and harder. It's probably the hardest part of the induction proof. So what I like to do is I like to see which one of my sides is more complicated, or the one that I can get the most out of. So I know that this side here, if I expand it, I can get n squared plus 2n plus 1. Okay, so that's one option. So in my head, I'm saying, okay, well, I can get n squared plus 2n plus 1, okay? And that's helpful because I have an n squared and maybe an n squared there, so maybe that can lead to something. In this case, I have n plus 1 factorial. Well, the only thing I can really say from n plus 1 factorial is that, that's helpful, is that it's n factorial times n plus 1. Okay, but then I have n factorial. Okay, I know that that's greater than n squared, but then I get an n cubed, like I get an n squared here, and then I get an n cubed, and that won't really help me. So it seems like it'll be safer if I start with this side. Okay, so that's what I'm going to do. I'm going to start with my left-hand side. Okay, so my LHS is equal to n plus 1 squared. And let's just open that up. That's n squared plus 2n plus 1. So that's just a plus b whole square is equal to a squared plus 2ab plus b squared. Okay, and right away I'm going to use my inductive hypothesis. I'm going to say that that's less than or equal to n factorial plus 2n plus 1. Okay, so this is my inductive step. Again, if you're confused how I get my less than or equal, I'll do another aside. I did this in another video, but I'll do it again. So if I say, let's say I say A is greater than or equal to B, okay? And I'm saying A plus C and B plus C, right? So C is obviously the same thing as C. So the only thing that's different between these two statements, the only thing that's different is this A and this B. But since A is greater than or equal to B, then that means this whole statement is greater than or equal to this whole statement, right? So that means that A plus C is greater than or equal to B plus C, right? And so it's the same thing here. This is like my C, it's like my C. This is like my A, and this is like my B, okay? So hopefully that's clear. Now, the next thing I'm going to do, again, this might not seem obvious to you, but you'll see why. So I have a 1 here. Now, a 1 is it's not really practical because I want to sort of get to a situation where I have only n's in my expression. And remember, in my inductive hypothesis, so when I assume that Pn is true, I also assume that n is greater than or equal to 4. So necessarily that means that n is greater than 1 or greater than or equal, right? So because n is greater than, so this is another aside, because n is greater or equal to 1, n is greater or equal to 4, and 4 is greater than 1, then I can just say n is greater than 1. But for the purposes of this sort of situation, I can just say n is greater than or equal. Okay, so that's what I'm going to say. I'm going to say that this statement here is smaller than or equal to n factorial plus 2n plus n. Right, that's perfectly legit because I know that n is at least 4, and 4 is clearly greater than 1. So this statement, the greater than or equal to, applies. Okay, so this is because n is greater than or equal to 4. Okay? So that's equal to n factorial plus 3n. Okay, now, remember what I'm trying to get at. I'm trying to get at something that looks like, n plus 1 factorial. So if you want, again, n plus 1 factorial can be written as n factorial times n plus 1. Well, I have an n factorial here, and I have an n here. So ideally what I'd like to do, I'd like to get another n factorial, so I could factor an n factorial on this and this term and get an n plus 1. Right? Because now what I'm searching for a way to use this as sort of a common term. Because if I want, I can sort of re-multiply that, and I'll have n factorial n plus n factorial. So n factorial I already have. I have an n. The only thing I'm missing is another n factorial. Well, what I can say, and this is going to be again here. So since n is greater than or equal to 4, right? Well, that means that n factorial is at least going to be 24, right? And so n factorial is greater than or equal to 24 because that's 4 factorial. This is 4 factorial. And so that's clearly greater than 3, right? So I can say here that this statement that I'm about to write is greater than this statement, n factorial plus 3n. If I say that n factorial plus 3n is less than or equal to n factorial plus n factorial times n. Because I just said that since n is at least 4, then n factorial is at least 24. So strictly speaking, n factorial needs to be needs to be greater than 3. Okay, and now I just need to do a bit of rearranging, so I can write n factorial as a common factor, 1 plus n. If you really want to be picky, I can write n factorial n plus 1, and that clearly by definition is equal to n plus 1 factorial. And so I've started with this. I've started with this guy, n plus 1 square. I went through an equal, but now automatically I have a greater than or equal. I have another greater than or equal, I have some equals, then another greater than or equal. So automatically, once I hit a greater than or equal, I can say that what I started with is greater than or equal with what I ended with, right? So this means that n plus 1 square is less than or equal to n plus 1 factorial. Okay, and so we've proved. So we've proved p n plus 1. Hence the statement Pn, which was, if you remember correctly, that n squared is less than or equal to n factorial for n greater than or equal to 4, that this statement is true by mathematical, we'll just write it shorthand, induction. So there's another example on a proof by induction with regards to an inequality.